Okay, so continuing on with our discussion of Android, what we're going to talk about now are the so-called middleware infrastructure layers. And there's actually multiple layers here. And basically, the purpose of middleware is the number of purposes of middleware, but the purposes of Android's middleware infrastructure is to provide a higher level abstraction that shields the upper level services and applications from the lower level details of the operating system and the hardware. So it's all about raising the level of abstraction by which you program. And we'll talk more about what middleware is later. So the three things we're going to talk about are Hardware Abstraction Layer, or the HAL, the Android Runtime, and the so-called Native Libraries. And as you can see, visually, these layers are atop the Android Linux kernel layer. I also put a little bit of note here. Linux kernel, the Android Linux kernel is written primarily in C. The stuff that's available here is largely in C and C++, with some Java. And actually, the color coding here tells you a bit about the language. So if you see something that's red, that probably means it's C. If you see something that's green, that probably means it's C++, or maybe C, but more likely C++. If you see something that is blue, that means it's in Java, or the Java native interface. And then the yellow stuff is a little different. That's primarily C, but it's not part of the operating system kernel. OK, and we'll also talk about the key app components in Android. I'm going to give you a really quick overview of them, but we won't have time to discuss them at all. And we'll also perhaps talk just a bit about what Java threads are, although that's a much more detailed discussion later. So the purpose of the middleware infrastructure is to shield the higher level apps and app frameworks from all these weird hardware-centric capabilities of the operating system kernel and the underlying networking protocols and communication protocols. So we have this thing called the Hardware Abstraction Layer, and that shields the Android stack from low-level hardware details. You might go, gosh, that's kind of weird. Why do we have a need for a hardware abstraction layer when we have a kernel which has a device driver framework? Linux has a device driver framework, which Android Linux also has. Why do we have this hardware abstraction layer as well as the OS kernel, which is also a hardware abstraction layer? That seems a little bit weird at first glance. And there's a couple reasons for this. We'll talk about this in more detail later. In a nutshell, the reasons are, number one, that it helps to shield Android manufacturers, or the so-called OEMs, from the virality of the GNU public license, of the GPL. So the GNU public license comes with some strings attached. Most notably, if you combine your code with code that is GNU code, GPL code, then you are obliged to release all of your code in open source form. Not everybody wants to do things like that. In particular, the OEMs have come up with all kinds of clever ways of being able to provide encapsulations of their own specific hardware. And they don't want to have to give all that code away to everybody, because it would be a competitive disadvantage to have to give away all their code to all the other people who are also Android manufacturers. So the hardware abstraction layer, among other things, has a different licensing model, which allows the source code to remain hidden. You don't have to release the source code for things that are done in the hardware abstraction layer, because it's not done with the GNU public license. Now, there's a whole bunch of debate about whether that's actually viable or true or not, but let's leave that legal debate aside for the moment and just assume, for sake of argument, that things that are in the hardware abstraction layer are capable of being released by manufacturers in binary form only without releasing the source code, where anything that's linked in the Linux kernel must have the source code released. So that's one of the reasons. So that's the legal reason. The less legal reason is that there are certain things that the Linux kernel didn't really anticipate originally, because it wasn't designed for mobile devices. So like interacting with a radio is one of them, so for your cell phone calls. So there were certain APIs that the kernel provides, which are very simple. They're like open, close, read, write, ioctl. Device drivers in the Linux kernel have very simple interfaces. And for a variety of reasons, people building mobile apps wanted to have a higher level object-oriented interface as opposed to a low-level C sort of function-oriented interface or procedural interface. And so these interfaces here are defined at a higher level of abstraction using good old-fashioned method calls on objects and so on. So that's another more technical reason for having a hardware abstraction layer. There's also something called the Runtime and Libraries layer, which itself is composed of several middleware elements. As you can see, it's kind of got a bunch of stuff in green and a bunch of stuff in yellow and blue. So the Android runtime is one piece of that layer, and that itself is composed of two parts. So on the one hand, we have something that I like to call the managed execution environment, which originally was something called Dalvik, which was a virtual machine in the spirit, although not the style, of Java, classic Java interpreters with Java bytecode. It's a variant of that that has its own bytecode and its own architecture, but it's kind of in that same vein of a virtual machine. And then later they discovered that this had some downsides. As systems became more processor intensive, the interpreted nature of a virtual machine didn't really scale up to utilize the underlying hardware as effectively as people might have wanted, especially because there was this pesky competitor out there known as iOS that had better performance for a while. So they moved away from Dalvik, although it still lurks there in some vestigial elements, to something called ART, which is the Android runtime. And Android runtime, or ART, is something called a ahead-of-time compiled implementation of an execution environment. So what it does is it basically compiles as much of the code into binary as possible at compile time and doesn't rely as much on interpretation. Whereas Dalvik is more interpreted. It does have a just-in-time compiler optimizer built in, but that's typically, at least in theory, not as fast as a ahead-of-time compiled version. So most Java apps, or apps that leverage Java, like Kotlin-based apps, utilize the managed execution environment. And some of the Android system services also do that. And basically, anything that's written in Java or something that turns into Java bytecode will leverage this execution environment, one of these two. And then on top of that, we also have something else. We have the core libraries. And this basically includes a copy of the core Java class libraries, a copy of the interface code, basically the APIs. And then at one point, Google had rewritten their own implementation of those APIs. But more recently, they've moved to using something that's kind of a mixture excuse me, of their own implementation, plus lots of implementation that's been taken from the open source Java 8 version of Java. So the Java 8 platform, which is a bit behind the times now with, I think Java 11 is coming out shortly, but at any rate, they have a Java 8 implementation now, which is kind of a hodgepodge of various things. So they have a copy of the core Java class library, defining code, and then more recently a bunch of the implementations from JDK 8, plus their own implementations. And then there's also a bunch of core Android class libraries. And there's something like, I forget, 70-some packages from the Java platform, and there's like 100-some packages from the Android core library. So there's a lot of code in here. And one of the key things, of course, that's here that is interesting for this course and for the other course that I'll teach in the spring is Javathread. So all the Java threading support lurks here. And there's also other cool concurrency APIs that are provided with Android, things like the Hammer framework, handlers, messages, and runnables, or the async task framework. If you're able to come back next semester, you'll get a chance to learn about all that stuff because we'll have a whole other class that covers those kinds of things in more detail. Okay, so another thing that's important at this layer are all the components that are part of the Android architecture. So these are core components, we'll also talk about them in more detail. As I mentioned before, we have activities, which are basically where the user-defining code goes, user-facing code, things that interact with users, with dialogues and displays and so on. We have services, which can kind of run in the background and do things that may be longer running, like downloading files. There's broadcast receivers, which are used for handling event notifications. And then there's these interesting objects, which are really sort of pods, plain old data structures, called intents, and they're used to basically communicate between these other components and also are used by Android to launch those components. And then the final piece of the puzzle architecturally is something called a content provider, which is really just an abstraction for storing information persistently. So your emails would be something that could be stored in a content provider. Your text messages could be stored in the content provider. Your photos could be stored in the content provider. All kinds of things where you need to store stuff would be accessed and managed through a content provider. And then, of course, there's also lots and lots and lots and lots and lots more stuff. So there's a database called SQLite that's built in. There's all kinds of different ways of having widgets and user interface components, all the kind of stuff you'd expect when you're trying to build applications that interact with humans. We'll cover a lot of these things. We will not have time, obviously, in the few remaining classes to go through this stuff in detail. That's probably another 14-week course on its own. But if you're curious about it, you can take a look here at the Coursera website, which is the specialization that I developed with my colleagues, Julie Johnson, Jerry Roth, Jules White, and some other folks on Android app development. And there's also some other cool stuff that we've done in conjunction with the University of Maryland that go even deeper and talk about the user interface side of things, so you can learn how to program that stuff as well. Android, just like Java, tries to provide this balance between performance, runtime performance, and developer productivity. So in particular, one of the things to be aware is that many of the core libraries in Android are actually implemented in C or C++, and then they have these Java wrapper facades that give you an object-oriented Java interface to capabilities written in C++ and Java, C++ and C. And the reason for doing this is you want to be able to get high performance while still giving high performance, in other words, make the computer run faster, while giving people a programming model that looks and feels like Java and comes along with all the other nice things about building Java code. So a rather large amount of code in Android is actually developed using a JNI-like mechanism where the implementation is in C or C++, but the interface is in Java. And that, again, is intentional. It's kind of a trade-off to make things run faster. There are also a bunch of native C and C++ libraries above and beyond what's in the core libraries that mostly are available in open source form, and you can get access to them in a variety of different ways. A lot of the application framework components provide you with Java wrappers for what's in the native libraries. And if you are so inclined or so crazy, you can actually write chunks of your application in C and C++ using something called the Native Development Kit, or the NDK. Not a widely recommended practice because it pulls in all the accidental complexities of programming in C and C++, but it's available. The typical people who would choose to do something like this would be people who are building very high performance or performance sensitive apps, like gaming. So if you're doing some kind of using the Android platform as a gaming console, then you might choose to use the NDK stuff. But it's pretty rare, quite frankly. OK, so that's the end of the overview of the middleware infrastructure layers. And the key focus is on layers, because as you can see, there's a fair amount of stuff.